This split screen demonstrates the operational core of modern image generation, known as the diffusion paradigm. The mechanism maps a complex data distribution, like photographs of the real world, to a tractable prior of standard Gaussian noise via a Markov chain, and then reverses the sequence to resolve the noise into a distinct image. The core machine learning task is to train a neural network to calculate the exact reverse transition probabilities of that Markov chain, stepping backward from pure static to structured pixels. Managing trajectories of millions of pixels across hundreds of probability distributions presents a significant computational hurdle. The Denoising Diffusion Probabilistic Models framework handles this by reframing the problem as a simple L2 regression, where the model optimizes against the noise rather than the pixel values. Building on that foundation, a subsequent technique called Denoising Diffusion Implicit Models, or DDIM, utilizes a deterministic mathematical adjustment that breaks the strict Markovian requirement, accelerating inference by up to a factor of 50. The probabilistic foundation of DDPM and the acceleration logic of DDIM provide the structural framework used by most state-of-the-art vision architectures. This vector space illustrates the forward process, denoted as Q. It is a fixed Markov chain that iteratively corrupts a clean image vector, x0, by adding standard Gaussian noise at every single step along the timeline. The exact scale of corruption at each individual increment is dictated by a variance-preserving noise schedule, defined by the variable beta t. As the step count moves forward, this schedule scales up the amount of noise injected into the image. Executing this chain step by step during a training loop is computationally unviable. Generating the training targets for a neural network requires thousands of sequential operations per image. We bypass that bottleneck using a mathematical shortcut derived from probability theory. Because the sum of independent Gaussian variances is additive, we can collapse the entire sequence. By substituting in a new cumulative product notation, alpha bar t, we can sample the exact state of the image at any arbitrary step t directly from the ground truth training data, x0. We no longer need to compute the steps in between. With the forward process optimized, the system must learn the reverse process, parameterized as p theta. The objective is to train the model to maximize the log likelihood of the target data distribution. Calculating the true log likelihood requires marginalizing, or summing over, all possible trajectories from pure noise back to the target image. Because the vector space of an image is high-dimensional, that calculation is strictly intractable. The forward jump is mathematically solved. Making this architecture function depends entirely on finding a computable lower bound to approximate that intractable reverse trajectory. To bypass the intractable marginalization over all trajectories, we optimize against the evidence lower bound, or ELBO. Expanding the ELBO reveals several terms, but isolating the core of the equation leaves us with a specific calculation, a KL divergence. This KL divergence measures the exact mathematical distance between the true posterior distribution of the data, labeled Q, and the neural network's approximation of that distribution, labeled p theta. The distribution Q is defined by its conditioning on x0, the clean, uncorrupted image. During the training phase, we have access to this ground truth, allowing us to evaluate the forward corruption step at any point. We can apply Bayes' rule to the true posterior. By utilizing our known ground truth x0, Bayes' rule allows us to flip the conditional dependencies, converting the forward step into a reverse probability. Applying Bayes' rule expresses the true posterior as a product of known quantities. This results in a tractable Gaussian distribution with an analytically computable mean and variance. Next, we structure the architecture to align with this finding. We define our parameterized neural network model, p theta, to also output a Gaussian distribution. Because both Q and p theta are now Gaussians with fixed variances, the KL divergence between them collapses into a direct comparison of their means. We are simply measuring the distance between the actual noise we injected and the noise the model predicts. This yields the final DDPM loss objective. The network does not need to predict the final image itself. It only needs to execute an L2 regression to predict the specific noise, epsilon, added at that step. To properly calibrate this prediction, the neural network requires two inputs: the current state of the noisy image and the exact time step along the sequence, telling the model how corrupted the vector currently is. The mathematical elegance of DDPM relies entirely on using Gaussian distributions to collapse a high-dimensional, impossible probability integration into a highly scalable, isolated regression task. While training is optimized, this timeline exposes the primary bottleneck of standard DDPM during inference. To generate an image, the model must sequentially evaluate the network for all t-steps, often 1,000 separate iterations, injecting stochastic noise at every single increment. Simply skipping steps to save time causes the model to fail. The inherent stochasticity between each step creates a multiplier effect. When gaps are introduced, those variances accumulate into compounding errors that destroy the final image structure. The foundational insight of DDIM solves this by altering the forward process. If we construct a new sequence of distributions that matches the exact same marginals as DDPM, as shown in this constraint equation, we can utilize the exact same pre-trained neural network. DDIM defines a family of non-Markovian forward processes. These processes are parameterized by a new, adjustable variable representing variance, denoted as sigma. The acceleration occurs when we execute the formula by setting sigma to 0. By doing this, we mathematically erase the stochastic variance term from the process completely. With sigma at 0, the reverse process becomes entirely deterministic. Randomness is strictly localized to the starting noise. The path back is entirely fixed. By removing the probabilistic requirement between adjacent steps, DDIM unchains the generation process from the strict Markovian sequence. It modifies the math of the transition without requiring the expensive retraining of the underlying model. Charting this deterministic formulation onto the timeline allows inference to operate over a much shorter subsequence of steps. We transition from calculating all t iterations to taking large, clean jumps across a subset we call S. Because no stochastic noise is injected at the intermediate intervals, stochastic drift is mathematically eliminated. The model draws a rigid, unbroken trajectory from pure noise to the clean image. In operational terms, this specific architectural adjustment compresses the generation phase, yielding a 10 to 50 times acceleration in raw inference speed. Bridging larger gaps without intermediate updates degrades the model's estimation quality slightly. However, by eliminating the compounding errors of stochasticity, that fidelity drop is manageable. To quantify the trade-off between estimation quality and generation speed, researchers rely on a standard evaluation metric called the Frichet inception distance, or FID. Empirical testing confirms the math. Evaluated against FID scores, a model operating at a 20 times speedup remains highly competitive against an unskipped, full-sequence baseline. The performance of DDIM proves a highly effective machine learning principle. You do not necessarily need to retrain a massive network to accelerate it. You only need to optimize the mathematical logic of how you traverse its learned distributions. Placing these algorithms side by side reveals their structural contrast. DDPM relies on a stochastic Markovian chain that requires slow, sequential execution. DDIM utilizes a deterministic, non-Markovian process to achieve high-speed generation. When seeded with the exact same initial noise matrix, the physical outputs behave differently. DDPM navigates a cloudy, wandering probabilistic path to discover the image. DDIM locks in a straight, precise trajectory to reach its destination. DDPM solves the tractability problem of high-dimensional generation. It leverages the evidence lower bound and Gaussian probability rules to make training neural networks on visual data mathematically feasible. DDIM solves the operational speed problem. It proves that the step-by-step nature of the forward process does not inherently require a strictly sequential Markovian reverse process during inference. By separating these two layers, the architecture decouples the training objective from the generation speed. The model learns the noise profile in one format, and we extract that profile using a different format. Mastering this specific mathematical duality, establishing tractability through the e-elbow, and driving acceleration through implicit distributions, is the bedrock for engineering state-of-the-art vision models.